Hi there, thanks for joining us again. This is Space Nuts, where we talk astronomy and space science. And my name is Andrew Dunkley, your host. Great to have your company. Now, normally I'd be joined by Professor Fred Watson, but he is away visiting family at the moment. And because he was going to be away and then I'm going to be away, and we tried to cram episodes in and we just couldn't do enough in the amount of time we had. We invited Professor Jonty Horner to join us, and we're going to do some specials. You might have heard the last one, which was very engaging and interesting and fascinating and long. This time, we're going down a different road. We're going to focus the whole program on astrobiology. Strap in, we'll do that right now.
15 seconds, guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here he is again, Professor of Astrophysics at the University of Southern Queensland, Jonty Horner. G'day, Jonty.
G'day, how are you going?
I'm well. Good to see you again. And we've got a lot to talk about, so I think we're going to just dive on in. Now, in preparation for this astrobiology chat, you sent me a paper that you wrote and published on the archive website. It's
ancient.
Yeah, it's coming up on 16 years since you wrote that. But one of the interesting parts was, look, it's been a couple of decades now that we've been finding exoplanets, and as technology improves, it's only a matter of time before we start finding Earth-like planets, and that's really going to make the search for life beyond our solar system really, really interesting. So those 16 years have passed. Have we got the equipment yet? I suspect we have.
It depends where you're looking, I think. I mean, in terms of looking at the planets around other stars, we can now learn a lot more about them than we could 16 years ago when I wrote the paper, that particular paper. But we're still not there yet. And it's a perpetual thing. No matter how hard you work, there's always more to do. The other thing that goes along with it, which I think is worth saying right up at the very start, is searching for life elsewhere is going to be one of the hardest things we've ever done. And absence of evidence is not necessarily evidence of absence. What I mean by that is we could, in a remarkable turn of events, in the next few months, find life elsewhere. You know, that's kind of the ultimate extreme, soonest possible. Very unlikely to happen. Alternatively, we might still be looking in a century. If we're still looking in a century, that doesn't mean that there isn't any life out there. But what it will suggest to us is that life is relatively scarce. So to me, the sooner we find life elsewhere, that it will be awesome because, hey, look, we found life elsewhere and we've answered the ultimate question, are we alone? But the sooner we find life elsewhere, the other thing it's telling us is that life must be fairly common in the universe. The scarcer life is, the harder it will be to find, and therefore the longer it will take us to find. And now the ultimate extreme of that is that this is the only place that there is life. And it'll be very hard to conclude that. Even if we were talking through a time warp in 10,000 years, when humanity is taking its fledgling steps into the galaxy or whatever, if we haven't found life by then, we'll be confident that life is very rare and very precious. That doesn't mean that there is not life somewhere else in the universe. And it's one of the challenges with this. I would like to think that we'll find the answer to that question in our lifetime. But the only way we'll get an answer to the question, are we alone, within our lifetime, is if that answer is no. If that answer is that there is life elsewhere. And this is one of the big, really, really big open questions for humanity, open questions for science. You know, when I was a kid, when you were a kid, one of the big questions was, is the solar system unique? Or are there planets around other stars? And we'll talk about that more in the next episode. But there is nobody under the age of 30, 31 alive on this planet that grew up in that shared universe with you and I. So that fundamental question got answered, and answered in abundance. And answering that question is the first real step to say, is there life elsewhere beyond the solar system? Because in order to find life beyond the solar system, we first need to know that there's somewhere that life could exist. The question of life in the solar system is a different one, and that's all part of astrobiology. So if you bundle all of this together, that question of are we alone, is there life elsewhere, which brings with it questions like, what is the origin of life? Why are we here? How did life begin? How did it get established? What are the processes needed? Everything like that is what gets bundled in astrobiology. And astrobiology is a very, very weird science. I know certainly early in my career, a lot of older scientists viewed astrobiology in a similar way to the way a lot of astronomers view astrology almost. You know, they viewed it as being speculation, fiction, and, you know, total bogus waste of time stuff.
Bollocks.
But it really isn't. Yeah, but one of the real challenges is it's not a question that one single discipline on its own can answer, right? It's not like in astronomy you're studying how stars form, so you talk to astronomers. In astrobiology, if we're looking at everything to do with life, astronomers like myself can't do it on their own. Biologists can't do it on their own. You need geophysicists, you need chemists, you need every area of human scientific endeavor to come together, because as scientists, our knowledge is somewhat siloed. I think I've said in previous episodes, the further you go away from what your speciality is, the more out of date and the more superficial your knowledge is. So I always view my knowledge as being almost like a Christmas tree shape. I've got a lot of knowledge about a very narrow area at the top, and the further you go from that area, the less knowledge I have, but the broader my knowledge base gets. And I think every human's like that. And you can almost imagine that if you're trying to answer the question of what you need for life, where we should look, which is what we'll talk about a lot today, you need a level that's above a certain point on that Christmas tree of knowledge to be able to contribute to that from a scientific advancement point of view. And the area that you can cover yourself is generally fairly small. There's a lot of knowledge that is needed that is outside your silo. And so that's where the interdisciplinary nature comes in. No one discipline can answer it their own. And that means astrobiology conferences tend to be mind-bogglingly bonkers, and you get people from very different disciplines along. And you learn a lot that updates your knowledge from when you went to high school. You also learn a lot that isn't about the science, but is about the scientists. And it's really interesting because we all think we're individuals. It's like that Monty Python thing, isn't it? We're all individuals, and there's a voice at the back that goes, I'm not.
I'm not.
Yeah, it's a bit like that. We all think we're all individuals, and we're very unique in the way we think and the way we present. But when you go to one of these conferences that's so multidisciplinary, the different disciplines present in different ways to one another, but within the discipline there are similarities. You know, so if you see the talks I give, I have beautiful pictures and bright text, white or yellow on them, limited text, usually a dark background, and that's really common for astronomers. You go to a talk by a kind of plate tectonics person, and suddenly you've got this mishmash of colours on a totally different background, where there's a bit more text, but the colour schemes are a bit, to me, kind of psychedelic and like something you'd see out of a 1970s cartoon, you know, because they're used to working with these geological maps that have a very different colour palette and sensibility, I think. And then you get talks from the biologists where they've got the name of one bacterium and it fills half of the page because it's such a lengthy scientific name, and they've got loads of text. And so you learn a lot about how what you study at university and what discipline you go into trains you to think and trains you to problem solve, because it trains you in a lot of different ways and essentially programs people. You know, I find that side of things really fascinating because it's a good way to learn to improve your communication skills. And you also pick up all this abundance of, wow, I never knew that, you know, and that's what we need if we are to answer questions like, how did life begin? Where did life come from? Are we alone?
Yeah, and that's really an interesting question, because it could be life not as we know it. Like we're assuming carbon-based life forms, but there could be life forms that have been created out of a completely different soup mix. Two things I want to get out of the way quickly. The Drake equation, which was created to try and assess how much intelligent life that was able to communicate existed in the universe, and the answer is still one. And the Fermi paradox, which says, that statistically there's a high probability of extraterrestrial life. So where is everybody? And that's what astrobiology is, really, isn't it? Where is everybody? And will they be people or will they be microbes? And I suppose my first question to you is, you're talking about finding life outside the solar system. Aren't we likely to find it first within the solar system?
So that's a really good question. I was going to talk about that a bit as well, because I think there are two different places in a broad sense we're looking for life elsewhere. One is in the outer solar system or on Mars, in our solar system, on one of the planets or on the icy objects. And the other is beyond the solar system. And those two things have very different characteristics. What I mean by that is that objects that are in our solar system are in our backyard. They're the only things in astronomy that we can get up close and personal with. So in the solar system, the search for life elsewhere is being driven by robotic exploration in the main. Yes, there's a little bit of observation from Earth. We saw that with the phosphine story on Venus that I ranted about a little bit last week. And the wonderful caution shown by scientists that was not necessarily reflected in the coverage. But a lot of the search in the solar system is robotic in nature. We send spacecraft to places to study them up close and personal. And we can't do that around other stars. Around other stars, it's very much a remote sensing type deal. So there are different ways of doing it. Now, I think there is a realistic chance we'll find life elsewhere in the solar system. There's a lot of good reasons for that. Now, before I dive into that a little bit, I'll just take a step back and come back to that point you made about life like us and carbon-based life versus other things, because it's really important to make explicit what is normally an implicit bias when scientists are talking about astrobiology. It's really made clear when you think about NASA and ESA's efforts on the moon, where they have on Mars, where they have aggressively said the strategy to look for life is to follow the water. What they're doing there is making an implicit assumption, that is an assumption that is not always written out and is clear, but is at the back of it, that life that we look for will be life like us. And I mean, life like Earth life. Now, we can imagine, you see it on science fiction all the time, you know, life that is very other. It might be molten metal monsters on a magma planet, or it might be an intelligent hydrogen cloud that nevertheless wants to flirt with Captain Kirk. It's very different kinds of life. But fundamentally, we only know of one type of life that does exist, and that's life like Earth life. And so when we look for life elsewhere, at least in what is the early stages still, it is really important to look for something that we know can exist and does exist, rather than looking for things that we could speculate might exist. If you've got to focus your efforts with limited resources, it makes sense to follow the kind of well-trodden footsteps of what we know about life on Earth. And from an astronomer's point of view, life on Earth needs three things. You know, it needs liquid water, it needs a source of energy and a source of nutrients, and quite often those two are the same thing, but not always. And wherever we find those things on Earth, we find life in abundance. And once life gets there, it's really hard to get rid of. You know, anybody who's had ants getting into their kitchen, or the mice plague that we talked about last week, knows just how life, once it gets established, keeps going. And so it makes sense, and a lot of what I'll talk about for all the rest of the episode is kind of based on this assumption that we're looking, at least initially, for life like us that has the same needs as us, where the us is the entire panoply of life on Earth, rather than us, as in me and thee, having this chat back and forward. What that leads to, though, is a lot of studies that have been done for the solar system are very water-driven. And if you go back decades, you could go back to the late 1800s when people were obsessed with this idea that there was an advanced technological civilization on Mars that was running out of time because the planet was desolate and barren. And this was all motivated by the observations of the canali, the channels on Mars that don't exist, which were mistranslated as canals. And canals on Earth are a very clear sign of human activity.
Yeah.
People at that time were so certain that we'd already found life that when there was a prize awarded, a prize laid out, and announced, I think it was like in 1899 or something, for the search for life, for the first person to discover life elsewhere, to find evidence of life elsewhere. That prize explicitly excluded Mars because it was felt that life on Mars was so well established that that was a no-brainer. You know, it was such a thing in popular culture that when the War of the Worlds broadcast happened in the 1930s, people thought it was live news coverage and panicked.
Yes.
You know,
the night that panicked America.
Yeah, and there's this whole heritage of our expectation of life being common and it being life like us requiring water. When we went to Mars, like in the 1960s with spacecraft, Mars was shown to be the desolate, arid world we knew today, and that put to an end the thoughts of an advanced civilization there. And from that time onwards, there was a period where arguments in astrobiology fell very much out of favour, out of fashion, and it was kind of viewed much more likely that life was almost unique. We were alone. There was no way you could look. And there's this argument that I often hear espoused that water is scarce in the universe. And that makes my head hurt. I think this is one of those big myths that is a myth of miscommunication or a myth of language being a personal thing. What I mean by that is, and I'm always trying to be very aware of this when I'm as a communicator, that words have different meanings to different people. And so the same word that I say, you'll hear, and it doesn't always mean the same thing to you or me. And one of the best examples of this is when you get people who are trying to argue against an area of science, maybe vaccines, maybe climate change, maybe something less controversial. You'll often hear people say that, well, climate change is just a theory, or vaccines are just a theory, or the Big Bang is just a theory. And to a lot of people, a theory just means a loose idea. A lot of people will say, why isn't your car starting this morning? Well, I've got a theory. To a scientist, a theory is a very different beast, and it's tied to the ability to make testable predictions and repeated testing. There's a lot of philosophy of science. I did a philosophy of physics course at university when I was 18, and I wish I'd done it when I was at the end of my degree, not the start, because I'd have got a lot more out of it. But there are people who've aggressively studied the philosophy of the scientific method. And even that philosophy varies a little bit discipline to discipline. A lot of other disciplines that are the experimental ones are very much more hypothesis-driven than astronomy, where we say, I'm interested in what this is, let's have a look. There's not really a hypothesis, I just want to look at it and find out. At least that's how I work. But you also have this thing where, at least from my philosophy, you can never prove a theory, but you can disprove a theory. What I mean by that is if you test a theory 1,000,000 times, and each time it backs it up, you haven't proven that theory. You've just shown that theory is a very good approximation to what's actually happening. So take the example of me flipping a coin. I can have a theory that says coins will always land heads or tails. Test that 1,000,000 times, and odds are 1,000,000 times you'll land heads or tails. But you've not proven that theory, you've just said it's a very close approximation to the truth. You could toss them 10,000,000 times, and one time your coin lands on its edge and balances.
Yeah.
That one observation, so as long as it's well documented and is repeatable, is enough to kill that theory, and then you need to develop something more complex. That's where it goes from. Now, that's a very roundabout way of coming back at this water being scarce myth. I think where that comes from is when you talk to me about water, I am just thinking about the molecule. I'm not thinking about the physical state. So to me, water can be water ice, it can be liquid water, it can be water vapor. But to most people, if you say water, they visualize liquid water.
Yeah.
Right? If I say, would you like some water? You're not expecting me to immediately start steaming your face. You're expecting a glass of water, right? What that means is that when people look out at the solar system and look everywhere else, we see this thing that Earth is the only place where we have abundant liquid water all the time on the surface. And so people have this idea that water is scarce, where what they're really thinking is liquid water on the surface of an object is scarce. But that drove a lot of this idea that life will be scarce because life needs liquid water on Earth. The Earth's the only place with liquid water, ergo life will be scarce. That's moved on, though, in about the last 3 or 4 decades, partially with the exploration of Mars, where we're getting an overwhelmingly greater amount of evidence that Mars in the past was warm and wet, that it had oceans and lakes. They may have been slushy or they may have been properly liquid, but it had oceans and lakes for a long time of liquid water. And we've even got evidence that there is permanent liquid water on Mars as we're talking now in the form of liquid water in the Martian polar ice caps. And you get temporary liquid water running on the surface. The other thing we found in the solar system is liquid water in astonishing abundance in the outer solar system, protected by shells of ice on the icy satellites of the giant planets, on the dwarf planet Pluto or inside the dwarf planet Pluto, probably in the larger Edgeworth-Kuiper belt objects, trans-Neptunian objects, maybe in other places as well, even in places as small as Enceladus. So there's been this revolution from the point of view of the solar system through my lifetime that actually liquid water isn't scarce. Coupled to the fact that the Earth is actually remarkably dry as a planet, that suddenly opened up people's perspectives again that the solar system is a good place to look for life. And that's driving a lot of exploration, a lot of missions, all the Mars exploration, past and future, focused around that idea. The fact that we've got 2 missions going to the Jovian icy satellites at the minute, JUICE and the Jupiter Icy Moons Explorer and the Europa Clipper, which are to characterize those moons better to prepare for potential future landings in the 2040s or 50s to get through the ice and look at what's underneath. Yep. We've got the Dragonfly mission going out to Titan, launching in a couple of years' time, probably next year, hoping to get there 2034, that will land on the only other place that has liquid on its surface exposed to the atmosphere in the solar system, and that's Titan with lakes of liquid methane and ethane. The water there is harder than granite and makes up the mountains. But there's this huge effort to explore our solar system and actually go there and look, which we can't do when we're looking at planets around the stars. And by going there and looking, if there is anything there, past or present, eventually we'll find it. Now, that immediately then poses a really fascinating one. So if we find life on Mars, or we find life on Europa, if we can look at that life and figure out its heritage, figure out its DNA, and I'm not a biologist, so I'll be a little woolly on that, it will be very quick and very apparent whether that life has a shared origin to life on Earth or whether it has a separate origin to life on Earth. Now, the separate origin would mean that life got started simultaneously on two objects in the same planetary system in an icy backwater of a fairly unremarkable galaxy. If it got started two places side by side, surely that means life gets started more easily than we expect. Therefore, life should be common in the universe. That would be an obvious logical continuation. The other option is that we find life elsewhere in the solar system and it has a shared heritage to life on Earth. What that means is that we analyse its makeup, we find that it has DNA like Earth DNA that has a shared universal common ancestor. And what that suggests is that once life gets started somewhere, it's transmissible. You know, you've got that old thing of don't go near Earth, it's got humans, they're contagious. This is the same kind of idea. If we find life on Mars and that life has a shared heritage with life on Earth, that validates, strongly supports the idea of panspermia, which I've had a student just submit his PhD thesis studying, the idea that life can transfer between the planets. Now, again, if life can transfer easily enough to be found in multiple locations in the solar system from a single origin, and maybe even Earth wasn't that origin. You know, maybe we're Martians, maybe we're Venusians or Venerians. I think that Venerian used to be the adjective for Venus. Adjective, the right word? It used to be the word for Venus in the way that Martian was for Mars, but it was a bit too close to venereal because... So they changed it. But anyway, but we could be venereal creatures. We don't know. But what that suggests is that if life is transferred easily and effectively once it originates, life could be common in the universe. So to me, finding life in the solar system would be awesome. I think it's eminently feasible. And either way, it will shed new light on the commonality of life beyond the solar system. We will be looking for life like us. It is possible to imagine life that is not like us, that has different requirements, but that will probably be a bit harder to find. And we don't know what it would be. Whereas with life like us, we know things to look for. So that makes it a bit easier for us to look for life like us. It also makes it, I'd say, a little bit stronger as a case when you're asking for funding, because you can say, well, we already know this kind of life can exist. So we're going to look at a place where the conditions are similar to where we know it does exist and see if we find it there as well.
Okay. Let's take a short break. This is Space Nuts with Andrew Dunkley and Professor Jonty Horner. Let's take a short break from the show to tell you about our sponsor, NordVPN. Let's talk about your online security. Now, I can tell you from personal experience, last year when Judy and I were overseas, we ran into a bit of a frustrating issue. There were certain apps we simply couldn't use without a VPN connection, things like our banking apps. They wouldn't load, and even a sports app I rely on wouldn't let me watch games back home because of geofencing and things like that. So with NordVPN, I was able to watch football back home while crossing the Atlantic Ocean. It was pretty weird, but it worked. And NordVPN is the best in the business. With NordVPN, you can securely connect to servers all around the world, which means your apps think you're right back home, even when you're not. It also encrypts your internet traffic, hides your IP address, and keeps your personal data safe from hackers and trackers and anybody else who's trying to get at you online. And this can happen in public Wi-Fi situations, in hotels, airports, cafes, anywhere like that. The best part, it's fast. Thousands of servers globally, and their NordLynx technology allows you to run seamlessly. No slowing down. It is brilliant. Right now, you can grab the special Space Nuts deal through this URL, nordvpn.com/spacenuts. You'll get 4 extra months free plus a 30-day money-back guarantee. So there's absolutely no risk if you want to give it a go. That's nordvpn.com/spacenuts. spacenuts. Stay safe online with our sponsor, NordVPN.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Space Nuts.
It's not Professor Fred Watson at the moment. He's away. We've got Professor Jonty Horner, and we're talking astrobiology in this little special edition. One thing I heard in the news recently, and I think Fred and I talked about it, was we've been talking about water, and if you want to find the people, find the water, that sort of thing. But there was one particular study that was recently released that says if you want to find the people, find the coal. What do you think of that theory?
That's an interesting one. So that's the idea that if you want to find somebody to talk to, there needs to be something to fuel an industrial revolution.
Exactly.
And again, this is, I think science fiction sometimes does this really interesting questions of almost, is the path that we have followed the one that everyone will follow? Because there's so much, to some degree, randomness in the things that have driven our knowledge and our development of things, Obviously, a good example is a famous myth about penicillin, that if you leave your bread out and it goes mouldy, that makes your poultice more effective. And that was an incredible scientific revolution driven by that discovery there. Who's to say other civilizations would have the same discoveries in the same order? Now, to advance, we have required advances in energy in order to allow us to better develop technology and develop the things that everything's made of. If we didn't have anything that you could burn, it would be very, very challenging to smelt metal. If you couldn't smelt metal, how do you build electronics?
You are spot on. That's exactly what the article was all about. And the bottom line was that because of the timing required, it lessens the likelihood of us finding people like us. It reduces the odds.
And this is where there's a difference between the search for extraterrestrial intelligence and the search for life. So the search for extraterrestrial intelligence is like a subset of the search for life. Yeah. Search for life is a search for bacteria as much as it's the search for communicative aliens. And there's been a lot of stuff written and discussed about whether evolutionary quirks have benefited us by being here, in terms of we're a social communal animal that shares resources and shares learning. There have been other ones like that from ant colonies, and I'm listening to a very chill and very silly lit RPG, I think would be the description of the genre, series of books called Chrysalis at the minute, where a young boy who dies for reasons is reincarnated in the body of an ant, and it's a book about him as an ant and his life in the colony and stuff. And it's bonkers, but you've got an advanced social species there, and he finds ways, without too many spoilers, of giving them intelligence and what happens afterwards. Right. There's a few species in the history of Earth that have that kind of communal sharing of information thing. We're the only ones that have achieved what we've achieved. Some arguments are that's down to the development of language and our ability to produce complex language, and also the opposable thumb being quite important. So there's a lot of stuff that there are many steps between the development of life and the development of intelligence. And the development of intelligence itself doesn't necessarily mean the development of technological intelligence. A lot of discussions about all the things octopi or octopods or octopidals, octopi could achieve if they lived for more than 3 years and if they were a social animal. So they've got incredible brains. We're learning more and more about some of the brain power that birds exhibit. But none of them have become technological intelligences. And the search for extraterrestrial intelligence is very much centered around a technology that allows civilizations to communicate with one another, that therefore is based on many prerequisites that lead to the development of the ability to broadcast your existence to the cosmos. The coal thing's interesting. I mean, I'm not sufficiently archaeologically minded to be able to say with certainty that without coal we wouldn't have got here. And the reason that I express caution on that, coal and oil, is that we have things that people burn for energy that are not coal and oil. And I think a lot of the smelting that was done, and I may be wrong on this because I'm not an archaeologist, I just picked it up when my partner's watching Time Team and things like that. She loves her archaeology, so I get a little bit of that as a very thin veneer. But I think a lot of the times when people smelted metals, talking about bronze and iron, they used wood or they used charcoal, which is a byproduct of burning wood.
Yeah.
So maybe it would be more challenging without the easy available energy of fossil fuels, without the easy available energy of coal, oil, gas. But it might be that that wouldn't be an insurmountable hurdle, but it would result in a different path being followed. You know, what would we get in terms of steam power if we were using wood and if we were using charcoal rather than other things? Would it lead to an earlier adoption of renewable energy in the form of wind power, which was actually being used for hundreds of years? You go back to Europe and you see the windmills people use and water mills people use. So I don't know whether... And this is a problem with all of astrobiology, and it's a problem with a lot of the stuff that I'll talk about later about what makes a planet more suitable or less suitable. People have this tendency to find something that is unusual about us. And there's a lot that's unusual about us. I mean, there's a lot that's unusual about me, and I hold my hand up about that. But they find things that are unusual. And they say, we are, as far as we know, unique in the cosmos. We are a technologically advanced civilization able to have this discussion. There has to be a reason that we're here. Everything that is unusual quite often gets held up as, could this be the switch? If you didn't have this, we would not be here. And I tend to view them not as an on-off switch, but as a slider. They're like, and again, a gaming analogy would be varying the difficulty on your game. Some games, it's very kind of on-off, hard mode, easy mode. Others, particularly some of the role-playing type games people play, have sliders for everything. And so you can change things to the nth degree to tweak the challenge level. And I think all of these things, like the existence of coal, that get proposed as being a boundary, as being something that would be a block if you didn't have it, are actually probably more like one of those sliders. They're things that can facilitate, but it's really interesting to discuss them because we don't know how big a filter they are. We don't know how big a hurdle they are without digging into it more. And the more we can suggest these things, the more we can narrow them down. But ultimately, the only way we can finally test them is when we get a response to us, when we find technologically advanced life, and then we learn about their heritage. What path did they follow? Did they invent fire before the wheel? Did they invent modern medicine before fire? And I've seen there's a fabulous famous old thread. I don't know, it wasn't from Reddit, it predates Reddit, but from one of the old messaging boards that talks about humans as the horror movie monsters of the universe. Because we always, in science fiction, all the monsters we face, all the aliens we face are usually more something than us. And we overcome incredible odds to beat them. But this is taking the other perspective of another species kind of looking at us and going, those humans are terrifying, and it's listing all the ways we are. You know, we're an exhaustion hunter. We didn't beat things by speed or anything. We'd follow them until they died of exhaustion because we can go longer than they can. They were saying, you know, it's the only intelligent technological species that invented amputation before painkillers. You know, we've got things like this that are very bizarre about us. And so that takes this perspective I've got of these things are a hurdle, and you develop things, you know, that things are not an on-off switch, but they're more of a slider. And the idea of, will things naturally be developed in the same order? And turns it around and said, what would another species think looking at us? And I always find that really good fun. And it's effectively leads to the thing that humans are space orcs, and we're this terrifying, weird little species. And maybe that's what it'll turn out to be.
Well, look, I don't dispute that, because look how we treat each other, or have treated each other since civilization began. Basically, I don't think you could add up how many wars we've fought against each other. I don't think that would stop if we found another intelligent life form. I don't think we'd go in saying, "Hi, hey, we're really nice." I got a feeling there'd be a bit of adversarial.
It's a really
attitude.
It is a really interesting one. It's one of the things that people factor into a lot of the discussions about the rights and wrongs of active SETI. So active SETI is sending out a message saying, "Hi, we're here, please talk to us." Whereas passive SETI is listening for people saying, "Please turn neighbours off, we're sick of seeing it." You know, they're effectively the two ways you can do SETI. There are a lot of people in the past that have argued that active SETI is a bad idea because it will attract the wrong kind of attention.
Well, Stephen Hawking certainly thought that.
And throwing no shade, I think the great Mark Commode, who's a film reviewer in the UK, often says, other opinions are available. They're wrong, but they are available. I mean, this, I think, is a case of that. I think, if any, for me, and I will admit I'm an optimist, I'm also not exactly the world's most aggressive person. But for me, if you have survived as a species for long enough to be a thriving civilization to the point of wanting to communicate to the upstarts that are broadcasting, Big Brother and all the rest of it to the universe, that suggests that to some degree you've overcome your martiality. Because I think for us to survive to the point where we're moving out into the stars will require us not to first wipe ourselves out. And the more advanced you get, the more you disperse, probably, fingers crossed, hopefully, the less likely that becomes. Now, we look at the world around us today, and without digging into politics, there's always something nasty going on. There's many, many tragedies that are both frontline in the news and forgotten by the news. But I saw a great article a few years ago that was arguing that, when was the worst time to ever live, and saying that actually, despite the fact that all this war, all this aggression, all this violence is so front and centre, this is actually the safest era to live in that humanity's ever experienced. The number of people dying before their time, dying before they reach senescence, is lower per 1,000 people or per 100,000 people than ever before. You have a much lower chance as an average person of ever fighting in a war, of ever being murdered or assaulted. So we're already moving that way if it doesn't feel like it. And so to me, with that optimistic viewpoint, I would like to think that there is no reason for conflict and no reason for friction. And I think a lot of the arguments that humanity's future encounters with aliens must by necessity be violent is telling you more about people than it's telling you about aliens, because it's saying when we look in the mirror, we see the angry, snarling tribalist ape rather than the rational modern human that is a veneer on top. We're still a tribal species. We're still the product of our evolution. And society is a veneer that we put on top of that as we learn to be better, to be the kind of thinking social ape, I guess. And the evidence is that over time we're getting better at that, even though we're now more capable of killing each other than we ever were before. We're doing it less often.
Yes, we are. All right, we'll take a quick breather because I want to get into the area of finding this life beyond our solar system. How are we going to do it, where we're going to look, and what we've got to look for. That's all coming up on this edition of Space Nuts.
Roger, you're loud and clear here also.
Space Nuts.
So, Jonty, look, lead the way. Where do you want to go from here? We've got to. This is our final segment. So, I suppose if you're going to try and find life beyond our solar system, you've got to find the right environment. Rocky planet, habitable zone, perhaps.
Where do we
and there's a lot more to it than that. It's not just a planet with perhaps liquid water on its surface. You've got to have, I suppose, the right kind of star. You don't want a red dwarf because you probably just, get really bad sunburn. There's a lot to take into account.
There's a huge amount of depth to it. And I think, as we saw with the previous episode, we could have talked another hour. And we could have talked another week, to be honest. When we're talking about this stuff, one of the things I most adore about science is the infinite complexity. So you ask a question, when you get an answer, that isn't it, but you get another 10 questions. And the more you know about a subject, the more complexity there is. To me, that's just a wonder, and that's fascinating. And this is a really good example of that. Now, one of my strongest arguments through my career has been that we can't just, when we're trying to think about where we're going to search for life beyond the solar system, use a habitable zone and that's it. It seems like a lot of coverage and a lot of papers just go, Earth-like planet found in the habitable zone, whee! And that's about it. Now, the habitable zone has become a really effective communication tool in much the same way the Drake equation has. The Drake equation is this fabulous tool with all the sliders where you can make your own inhabited universe with lots or few aliens by varying the variables. The habitable zone has become another of these catch-all kind of visualizations, and it's born of the idea that life needs liquid water, with the implicit extension of that life needs liquid water on a planet's surface. Now, that's initially motivated by the fact that the Earth is the only place with life, and back when this was being discussed, the only place with liquid water that we knew. So therefore, it was natural to say you need surface liquid water. As we discussed earlier, there are plenty of places in the solar system that do not have liquid water on the surface, but do have it underneath. They've got soft centres. But the habitable zone says you need liquid water on the surface of a planet for that planet to be considered suitable for life, to be habitable. Now, that isn't entirely true, but for the purposes of this, it's still useful because life buried beneath ice is so hard to find that we can't find it in our own solar system because the ice is in the way. We wouldn't have a chance to run planets around other stars. So even though I think the habitable zone's a big oversimplification, I see merit to it because life on a planet's surface with only atmosphere above is much more likely to be detectable than life buried deep in the interior. So fair enough, we'll go with it. The idea of the habitable zone, though, is that the closer you are to a star, the hotter you are. The further away you are, the cooler you are. And just like Goldilocks in the Three Bears, which is why it's often called the Goldilocks zone, there's a place where it's just right. It's not too hot, not too cold. Yeah. And therefore there could be liquid water on the surface of the planet. Now, a lot of the time when people say a planet is in the habitable zone, that's often taken as meaning that planet could and potentially will have liquid water on the surface. But actually what it's saying is, if you took the Earth, as the Earth is today, and put it in that system, would it still look like the Earth? Would it have liquid water on its surface? Now, we've extended a bit beyond that. There are a couple of fabulous papers, a bit more than a decade old now, that set what are our very contemporary scientific mathematical definitions of the habitable zone that people use for their papers. And they take the flux from the star, take into account the different colours of the stars, and there are two versions. There's the optimistic and conservative versions, where the optimistic version is a wider set of distances and the conservative version is a smaller set of distances. But it effectively uses Venus and Mars as a rough inner edge in our solar system and then scales that window up and down depending on the kind of star you're around. Yep. But that illustrates immediately that this is an oversimplification, because you can do a thought experiment. Let's take our solar system. Venus is way too hot, Mars is way too cold, and the Earth is just right. All well and good. Swap Mars and Venus around. If you put Venus where Mars is, Venus's thick atmosphere and greenhouse effect would mean it would be warm enough for liquid water on the surface. It wouldn't have cooled as much as Mars. So Venus would be habitable on the surface outside the habitable zone. If you put Mars where Venus is, with its very thin and tenuous atmosphere, it doesn't have much greenhouse effect at all. Mars would potentially still be habitable where Venus is when Venus isn't. And so that's immediately pointing that this story is actually significantly more complex.
Yeah.
That you can't just say, let's calculate the habitable zone, let's calculate the equilibrium temperature on a planet, which is a temperature it would have if it didn't have a greenhouse effect, that it was a certain reflectivity and it was in equilibrium with the light coming in and the light going out. And if that temperature is from about -20 upwards, it's probably warm enough for water because, well, you'll have a bit of an atmosphere. To me, that's never been enough. Now, the reason it's really important, at least from my perspective, is that finding planets is hard. We'll talk about that in another episode. But once you find the first of something, astronomy history and probably every other form of scientific endeavour history tells us finding the first of something is hard. But once you've got one, you quickly find more and more as your technology gets better. Finding evidence of life on a planet that is similar to the Earth is fundamentally at least an order of magnitude, if not more, harder than finding that planet was. So it'll take time for our technology to get good enough to search comfortably for life elsewhere. So initially that search is going to be very restricted because we've got limited resources. So you're only going to be able to look at a few planets aggressively at first to try and tease out any indication of life. But you're going to have loads to choose from. How should you choose? Well, to me, it can't just be the habitable zone.
Yeah, that's a valid point. And we've reached a point where we've found thousands upon thousands of exoplanets and counting. Like, we haven't stopped. We're finding them more and more and more often, of all different shapes of sizes. Some rocky planets, they've been harder to find because they're usually much smaller and don't sort of indicate themselves like a gas giant does. But we're getting better at finding rocky planets. I suppose the big question is, given how much we are finding, how do you identify prime targets for life?
Yeah, and that is what the paper that I put together with Barry Jones back in 2010 was all about. So Barry was a very dear friend of mine. He was my boss when I moved to the Open University from 2006 to 2009. I think he knew Fred very well as well, so you can always mentioned to Fred that we talked about Barry. I started work at the Open University in 2006 on the day Barry was forced to retire by the government because he'd hit 67. So he hired me and promptly retired, but he kept working anyway as emeritus professor. And Barry and I did a lot of work on this during my time there. Barry unfortunately passed away a little bit more than a decade ago, so he's fondly remembered. I organise an award in the UK in his memory every couple of years. What we did in this 2010 paper was to essentially have the thought process we just outlined. So we're going to have a huge number of potential exo-Earths, planets that could potentially be Earth-like, that could be places to look for life. But we're only going to be able to search a handful of them initially. So what should we do to select the best target? Now, obviously, the closer the planet's host star is to the solar system, the easier the observations will be. That's just a fundamental thing of, if you're twice as far away, we only receive a quarter as much light from you. But also, if you're twice as far away, the separation between the planet and the star on the sky will be half as much, because the angle gets smaller the further away you go, essentially. And we will want targets that are far enough from the star in the sky that with future missions like potentially the Habitable Worlds Observatory, we can separate the light from the planet from the light from the star. So probably even more important than the habitable zone is this proximity thing. The planets in the main found by the Kepler Space Telescope won't be suitable for this search because they're mainly very far from the sun. And so therefore they'll be very hard to study. We want to look locally. That's a given. But we want to look for places where there is the possibility of liquid water on the surface, because that means that the life will be in contact with the atmosphere, and that might generate a signature we can detect in the atmosphere. And that's where the habitable zone comes from. But there's actually much more to it than that, I think. And I'm far from able to give an exhaustive list because I'm not an expert in all areas of astronomy. But we decided to put together a review paper, which about 32 pages long, probably a little bit outdated now because science has moved forward, but was saying effectively, you can't just use the habitable zone. We need to think about all of the different factors that can contribute to make a planet more or less suitable for life. Now, many of these have been in the past suggested as that on-off switch, and I do think that they're more sliders like the numbers in the Drake equation or sliders on a mixing desk. But there are a lot of different things that have been suggested, and as I dug into the paper, there were even more than I thought of. You can broadly break them down into 4 areas. The first is galactic influences. So the impact of the galaxy itself, where you are in the galaxy, stuff like that. You've then got stellar influences, so the role of the star. You've got the planetary system, and then you've got the planet itself. So they're the kind of 4 broad areas. The galactic influences one is probably the least useful and the least well constrained. But the idea of the galactic influence is tied a bit to a theory that's been put forward by a few people called the galactic habitable zone. It's an idea that ties back to the origin of stars and planets and also to the dangers that are experienced because of your environment. The idea that as time goes on, the universe is becoming more metal rich, and by that I mean enriched in everything other than hydrogen and helium, because generations of stars run their furnaces and turn the light elements to the heavy ones and put them back into the cosmos. You need a certain amount of heavy elements to form planets like the Earth and to have the carbon, nitrogen, phosphorus for life. So as time goes on, the universe getting more enriched is a good thing. But there's also possibilities that too much enrichment will change the chemistry, or it will make planet formation too easy. There's all sorts there. So you might have a sweet spot from that side of things. Now, in the middle of the galaxy, star formation occurs at a more rapid pace and stars live and die quicker. So you get faster change in the abundance of materials. So you can imagine we have this concept in astronomy called metallicity, which is the amount, it's usually measured in the amount of hydrogen compared to the amount of iron in a star. And that gives you a number on a logarithmic scale, and that is an approximation to when the star formed and how enriched the world was at the time. And as time goes on, things get more and more metal rich. Within our galaxy, you'd expect there to be a gradient in this. So the things near the middle will be much more enriched in heavy elements than things near the outer edge. And there's probably a sweet spot in the middle that moves outwards over time, where conditions to form planets like the Earth and planetary systems like the solar system are perfect. So that's part of the galactic habitable zone idea. But the other idea is that if you're too close in and the stellar density is too high, eventually the stellar density gets so high that the likelihood of life being exterminated by nearby supernovae or planetary systems being stripped and disrupted becomes too high. So there's always been this idea that location within the galaxy is important. The challenge to that is twofold. Firstly, the proximity argument. We're going to have to look at stars that are very nearby, which are all at the same distance from the middle of the galaxy as we are. So where you are in the galaxy won't realistically impact this search because we're going to be looking locally. The other thing, though, is that stars have a huge degree of mobility. There was a recent story talking about finding solar twins, stars that have the same chemistry as the sun, that may have formed with the sun, and a suggestion that the sun and other stars may have formed as much as 10,000 light years nearer the middle of the galaxy than we are now. Stars are getting scattered inwards and outwards. So seeing a star here now doesn't imply that it's always been here.
Yeah.
So the galactic influences, I'm not going to go into really any more than that, but it's worth knowing that they're there. It's worth knowing that it's a point of discussion and that there is good research going on about this. It's a really interesting area, but it doesn't, I think, impact our initial search for life because we're going to be searching our local area. So it's a bit like me saying I want to search for signs of life on Earth. It's a lot easier for me to search in Kingsthorpe, where I live, than to search in Mumbai or in London, places like this. You've got to look locally. Now, talking about that, what would I expect to find? The people in Kingsthorpe have not all, but many of them have a similar background to me, formed in similar ways with similar culture, all the rest of it. So it's not a great analogy, I admit, but we've got to look locally. So the galactic influences stuff is interesting, but I wouldn't say it is a big factor, but it's worth mentioning, I guess.
So that leads us on to, I don't know, finding the right targets. And if we do find those targets, what do we do then to look for potential life on those targets?
Absolutely, and that's a very hard question. Now, in terms of finding the right targets, there's a lot that comes into it from the star itself. Now, stars live very long lives. First question then is, how old is a star? Now, if we look at life on Earth, the oldest fossils on Earth that are widely accepted are about 3,500 million years old. They're in the Pilbara, which is about 1 billion years after the Earth formed. There are some that are older that are still controversial, possibly as old as 4 billion years. But if we take the 3.5 billion years as a threshold, and we do what we're doing with the liquid water thing, and we say we expect life to follow a similar path to us, the fact that it took 1 billion years for life to get established enough to leave fossils we could find possibly means that it might have taken a similar length of time for that life to modify its environment enough to be detectable from elsewhere. So we can put an arbitrary kind of timer here saying that any planetary system younger than, say, 1 billion years may have planets that are suitable for life, but that life might have not had enough time to get established yet. So that might immediately say that's not as good a place to look as a star that is more like the age of the sun, where life's had 4 billion years to get going. Now, tied to that is the fact that the lives of stars are very dependent on their mass. So the more massive a star is, the brighter it shines, but the shorter its life is. And at a very rough level, this number varies a little bit depending on the mass of the star, but typically the luminosity of a star is proportional to its mass to the power 4. So if you've got a star that is 10 times the mass of the sun, it will be roughly 10,000 times brighter than the sun. But these stars are burning their own material. They're turning hydrogen to helium, and they're made of hydrogen. So a star that is 10 times the mass of the sun will only have 10 times as much fuel as the sun, but it's burning that fuel 10,000 times quicker, which means it'll run out a lot quicker. And what that means is that the more massive a star is, the shorter its life will be, and the less massive a star is, the longer its life will be. That means that beyond a certain stellar mass, the star will die before that billion-year cutoff. So we can probably rule out the most massive stars. They'll just live fast, die young, and it's unlikely that life will get well enough established. On the flip side, the dim little red dwarfs will just go forever. Proxima Centauri will still be trundling along in 1 trillion years when we're a distant memory. So they might be a good place to look. The challenge there, though, is that those stars are quite active quite often. And to be in the habitable zone around them, you've got to be very close in because they're cold little embers. You've got to snuggle up to the fire. So there's a lot of discussion about the fact that M-dwarf planets around these coolest, smallest stars, are probably not ideal places to look for life initially. Few reasons. One is that activity, and a lot of discussions that the activity of red dwarfs when they're young could scour a planet's atmosphere away. And that seems to have possibly been backed up with the TRAPPIST-1 planets that all seem to be airless worlds. The other is that those planets, if they are close enough in to be warm enough for liquid water on the surface, would have to be tidally locked, like the moon is to the Earth, which means they'll keep one face permanently pointed towards the star and the other permanently away, which may make it harder to look for life on them. It might be the case that any life would be on the sunward side, and that's kind of hard to observe because when that side is best presented to us, it's near the star. So that's challenging. Another thing that factors into it ties into something called the faint early sun paradox on Earth. The lives of stars, they shine brightly. Their brightness is measured compared to their mass, but their brightness increases with time. Stars get more luminous as they age a little bit, and it's a slow process. But with the sun, we think the sun was 30% dimmer when it was born to how it is now. So that means the Earth at the time got 30% less energy, which would have put it with its current atmosphere too cold to support life. That was offset by the fact we had a very different atmosphere then and a significant greenhouse effect, which was lessened due to the influence of life, stripping out carbon dioxide, particularly from the atmosphere, and keeping us mostly there and thereabouts. But what that means is that if we find a planet now, and that planet is near the outer edge of the habitable zone, everybody will go, well, it's in the habitable zone. That's great. Whereas my question would then be, but how long has it been in the habitable zone? Because when the star was younger, it was a little bit dimmer. The habitable zone would have been closer in, and that planet might well have been outside it. So I don't necessarily think that that 1 billion year clock would start until the planet was in the habitable zone. So we'll probably then be able to rule some planets out on the basis of the fact that they could be in the habitable zone now, but they haven't been for long enough.
Yeah.
So the star has all these effects. Never mind the fact that astronomers often joke that 3 out of every 2 stars are in a multiple star system. Multiple stars are very, very common, and that adds a whole extra level of complexity, both to the understanding of the lives of the planets in those stars, but also in our ability to study them. Because you've got more than one star's light to factor in all close together, it's much nastier and much more complicated. So there's a lot of ways that the stars can factor in, and I think that's only a very, very broad brushstrokes view, but you can see how what I'm thinking is you can bring in all these different ideas and have them as a slider. This kind of star could have planets around it with life, but it's not as good a target as this one. Now, everybody could build their own algorithm out of this, but I'd like to think that when we're trying to pick the target, you take into account the star that it's going around, how active it is. Is it a single star? Is it old enough? All these kind of factors. And then you can start looking at the planetary system that it's in, and there's a lot to talk about there, I think.
Yes, absolutely. And in our next special between Q&A episodes, we will look more into the planet side of things. I guess just to conclude, I'll throw one at you, and this answer is always different depending on who you ask, but what do you think the odds are that we will find some form of life?
I'm an optimist. I think the answer to it will be yes, we will find some sort of life. I think the harder question is when. Now, if we find life in 1 million years' time when we're not even human anymore, but we've hung around, we've managed to survive, that's not very edifying for me and you because it's a long time to wait. But as I said earlier on, I don't think it's a question of if, it's a question of when, because I find it vanishingly improbable for us to be the only system with life. And it's a numbers game for me. You know, we've got a galaxy with between 200 and 400,000 million stars. There are more galaxies in the visible universe, certainly than there are planets in our galaxy, probably more than there are grains of sand in our galaxy, all of them with hundreds of thousands of millions of stars. To say that out of, if you run the numbers, you get sextillions, septillions, even octillions, bonkersly full-on numbers of planets out there, that we're the only place that got life, that tells you that life is effectively impossible and we're a fluke.
Yeah.
Now, that could be the case. If that's the case, what we've got here on Earth becomes even more precious, and there is an even greater incentive for us to keep an eye on what we're doing so that Earth is still capable of hosting life in the future. But I think in reality, life will actually be more common than that. And you don't need to be much more common than that for life to be abundant in the galaxy. Let's imagine that life is found on one planet in 1 billion. That's billion with a B, so 1 in 1,000 million. Now, we're finding that on average, all stars have planets, probably have a number of planets. So if we say roughly there are 10 planets per star, there will be 4 trillion planets in our galaxy. If 1 in a billion had life on it, that will mean there were 4,000 inhabited planets in our galaxy. Not a big number. The nearest one would be so far away, in that case, we wouldn't find life for a long time. But life could be common, and we still wouldn't find it. The more you increase that likelihood of life, the nearer the nearest examples will be, and the sooner we'll find it. And that's why I think proximity will tell us a lot about the probability of life. In that, if we find life, the next step is to figure out we are not alone. We know we're not alone. How common is life? Now, the other thing I think factors into it, I think is a lovely kind of sci-fi thing to discuss all the way through. You mentioned early on carbon-based life and technologically advanced life, and we drifted away. The one place where I think that life that is different to us is something we could possibly find is silicon-based life. Now, the reason for that is not from the point of view of silicon people who have evolved in the way we have done. I'm thinking more kind of second generation life. Now, our exploration of the solar system is done by our robot envoys, and we're sending them near enough to home that we can tell them what to do.
Yep.
But we are developing, to certain controversy at the current time, we're developing a greater and greater ability to develop things that can make decisions for themselves without human input. Things like AI and other systems. And if we get to the point where we want to explore around other stars, we'll need to develop spacecraft that have enough autonomy to make their own decisions. You go back to the idea, and I don't know what's happened to it in recent years, but the idea of Project Starshot, where they made a little spacecraft, shot them off with lasers, and then they got to Proxima Centauri in 25 years, traveling at 1/5 of the speed of light. You do that, they get to Proxima Centauri. If they've got to ask us what to do, they send a signal to us, takes 4 and a bit years to get here, takes 5 years to get back, and by the time it reaches them, they're a light year beyond the system, and it's like, well, too late. So we have to give them a certain level of autonomy, and the more complex their mission is going to be, the more autonomous it'd have to be, which leads to the very science fiction idea that when we move out beyond the solar system, if we move out beyond the solar system, we will be preceded by a wave of life that is not us, that is our life that has a creator. That creator is humanity, that is silicon-based life, that we send out, whether they're von Neumann machines, whether they are incredibly advanced AI machines without the capacity to reproduce themselves. We will send out artificially built silicon life forms. And again, there's a lovely, fairly low-stakes sci-fi series called The Bobbyverse, which follows that kind of idea in terms of future Earth. Well, guy in the current day dies but has invested in cryogenics, and his head is frozen, and he wakes up and is essentially put into a von Neumann machine and shot out into the stars. And that's a really interesting one because it's silicon-based life that is also human. I mean, figure that one out, but it's good fun. Following, again, that very dangerous assumption that other life would follow the same pathway we follow, and it seems like we are going down this AI and increasing complexity and increasing autonomy route. You then argue that other species sending out craft into the galaxy would send out autonomous, intelligent silicon machines before they send themselves out. And therefore, I think we're more likely, if we're ever to bump into aliens, to run into one of these probes or one of these machines rather than the aliens themselves. So I think there is a very real chance that if we find intelligent, advanced life, it could be silicon-based rather than carbon-based, but it's silicon-based life that was created by carbon-based life, which, leads to really interesting questions about philosophy and religion and all those kind of things, which are not my forte. But, it does ask interesting questions about origin and creation when you think about it from the context of that, which is one of the things that's driven, like I say, a lot of wonderful and wonderfully entertaining sci-fi over the years.
Yeah. Look, as you said earlier, we could talk about this for a week, but we can't. But I do want to direct people to your paper. If people are interested in reading your paper from 2010, it's called Determining Habitability, Which Exo-Earths Should We Search for Life? And you can find it on the archive website. Is that right, Jonty?
Yeah, so that was published in the International Journal of Astrobiology in 2010. So the ones who want the kind of scientific reference, it's International Journal of Astrobiology, volume 9, page 273 onwards. But if you find it on NASA ADS, it'll give you the archive link, which is the preprint version, which basically means it's in my formatting rather than journal formatting. And this is, it's actually a handy aside that I'm sure has been mentioned before. The way that a lot of science works has led to the creation of the most profitable and problematic companies in the world, which are the publishing companies. And so the way a scientist works is we do all this work, da-di-da-di-da, hooray, hooray, hooray. We then write a paper to tell the world about it. We send that off to a journal who gets another scientist to volunteer their time unpaid for free to referee it.
Yep.
Then they charge typically the scientist who's written that paper money to publish that paper for them, and then charge everybody for the privilege of reading it. So if I want to read the journal versions of my papers, fortunately universities have paid access to a lot of journals, but I'm fundamentally paying to read my own work. And this is not ideal, I think, partly because as a scientist, I'm paid by taxpayers' money. People are paying me to do this work. To me, it is really important that they know what we're doing. They know what they're getting for their money. And part of that is be a science communicator. And I encourage any scientists or budding scientists, don't just focus on the science, focus on communication as well, because if you do science but can't communicate it, no one will know what you've done. But to get around that, what we do in astronomy and what many disciplines do is that we put preprints up on a publicly accessible free place. And it's in astronomy, it's just accepted that with very rare exceptions, journals will let you do this. So when we get our paper and we've written it, some disciplines in astronomy will put the paper up on the archive when it's submitted. Some will wait until it's accepted by the journal when it's refereed. I've always waited till acceptance, but occasionally if you've made a big discovery, you want to stop somebody scooping, you put it up at submission. There's a growing effort by scientists to put it up at submission to actively solicit feedback from the community to improve the work, which is good. But those papers go up on archive, ARXIV.
Yeah.
Be very careful. There is another platform out there where the letters in archive are shifted around, which is where a community of people who espouse ideas that are not scientifically verifiable will put their work and publish their own little papers. It's a different thing. But archive is a repository of free to view things. So if you are searching for papers, NASA's ADS system is wonderful. When you click on a given paper in there, most of them, but not all of them, will have a line that says journal version or ADS version, but there'll also be a line that says preprint. And if you click on the preprint links, it will take you to the archive and allow you to read the paper for free. Just to be aware that that is a version some of the time before refereeing, most of the time after refereeing, but before publishing in edits, effectively. So the link you've got to that is the preprint version of that paper. The other caution I give to people is that it is 16 years old, so all of the areas I talk about in it have moved on. We've learned more. We can talk a bit more about it next time as well, but always when you read things, be conscious of the fact that science is fluid. Science changes, our knowledge changes. I see just in the news recently, Jason Isaacson, who's, I think, the head guy at NASA at the minute, who's a wealthy multi-billionaire type guy, is arguing that the US is wanting to strongly build a scientific case why Pluto should be restored as a planet because fundamentally we discovered it, so it should still be a planet, and Clyde Tombaugh would be turning in his grave. That is what it is. But it is important to keep in mind that science is fluid, it moves, whereas once something is published, that's static. So it's a window on our knowledge at a time, rather than necessarily the modern version. If I were to rewrite that paper now, there'd be advances.
Of course, absolutely. But yes, I think we're trying to arrange to put the link on the show notes. I'll just have to remind Hugh about that. We might wrap it up there, Jonty. Fascinating topic, and it's one we get a heck of a lot of questions about. So, hopefully there's a bit of information in there to keep people's minds whirring. Jonty, thanks very much. We will see you again real soon.
It's an absolute pleasure. Thank you for having me.
Professor Jonty Horner, Professor of Astrophysics at the University of Southern Queensland, standing in for Fred Watson. And thanks to Hugh in the studio. Hugh couldn't be with us today. He got a bit confused. We know of one planet where there is life. Hugh thought we meant that he was the only life form on the planet, so he didn't see any need to turn up today. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.